All right, so we're going to finish this stuff off, and then we are going to go through your two quizzes. And your test is on Thursday on chapters 7 and 8. So the last application that we can use this exponential function formula for, and we've done some questions already with growth and decay, so we'll just do some more. So again, that's the formula you're given. Y equals a times b to the power t over p. It's on the formula sheet. Y is the final amount, A is the initial amount, B is the growth or decay factor, T is the time, and P, it says period time or the growth time. All right, so if you have a scenario where, let's say, the number of bacteria are doubling, then B, the base, your growth factor, will be 2. If something is tripling, then B, the base, or the growth factor will be 3. If you have a scenario where you have a half-life, where the amount of something is being decayed by a half every so often, then the base is a half. If you have an annual increase of 4%, okay, like an interest question, B is 1.04 because it's 100% plus 4% more. That's where the 1 comes from, 100% plus 4% more. Remember, in some cases, you might have an annual rate of 4%, but maybe it's compounded semi-annual, so you have to adjust your B value for that, which we will look at. If you have an annual decrease of 8%, that means you're maintaining 92% of what you had before. And so the B value will be 0.92, right? So those are some things that you have to remember. If B is greater than 0, you've got growth. If B is between 0 and 1, you get decay. That's a decreasing function. And we looked at that when we first started chapter 7. I'm looking at the graphs of exponential functions. So this warm-up says to determine the values of B and P for each scenario. If a certain strain of bacteria doubles every 4 minutes, that means the base is 2 because the number is doubling. And P, the time period for that to happen, or the growth period, is 4 minutes. Part B says if the half-life of a radioactive substance is 6 years, so B, the base, would be half. And there the growth period, or the decay period in this case, would be 6 years. If an investment triples every 10 years, then B is 3 because it's tripling. And the growth period there is every 10 years. And remember that T and P have to be in the same unit. So if P is in years, then T would have to be in years as well. T in this case would be, if you're going to figure out a problem with what the investment will be worth, let's say after 50 years, then T, the time, that's where the 50 comes in. But it triples every 10 years, so the growth period is 10 years. Population of a town is decreasing at a rate of 4% per annum, which means per year, so B would now be 0.96. If it's decreasing by 4%, that means it maintains 96% of its population. And then you have to change that to a decimal. And that happens every year, so your growth period is every 1 year. If the value of an antique is increasing at a rate of 15% per year, so that's 100% plus 15% more, that's 1.15 is your growth rate. And that happens every year, so your growth period, once again, would be every 1 year. All right? So, example 1, number of fish in a lake is decreasing at a rate of 7% each year due to overfishing. That's why B, the base, is 0.93. If it decreases by 7%, that means it maintains 93% of its population. So the equation is N equals 2,500 times 0.93 to the power T to answer the following questions. The fact that A is 2,500 tells us that is the population of the fish at this point. Right now, there's 2,500 fish in that lake. How many will there be there in 5 years? So that will be when T is 5. Because we're told T is the time in years. Actually, we're not told that. But you would be given that especially on a quiz test or on the diploma exam. Both variables would be defined. So that's 2,500. You can do this in your calculator all in one step. Times 0.93 to the power 5. So there's a population of the fish. Approximately 1,739 fish. How many years will it take for there to be half the original population? So if you have 2,500 right now, that means half of it would be 1,250 fish. That will be the final population. We need to solve for t in this case. We would do that by dividing both sides by 2,500, which will give us 0.5 on the left. And now to solve for t, we convert. We convert from exponential to logarithmic. We start with the base and cycle through. Remember, the base in both forms would be the same. So as a log, it would be log with a base of 0.93. And the cycling through tells us the order that the other pieces are written in. So after the 0.93 is the 0.5, and after that is our variable t. So the answer would be finding the log of 0.5 with a base of 0.93. So if you have the newer operating system, you can use that. If you don't, you have to use the change of base identity. So using the newer operating system, it would be 9.5, which you'd round to 6 years, or 9.6 years, I should say, to the nearest tenth. Using the change of base identity, it would be the log of 0.5 divided by the log of 0.93. So remember, by using the change of base identity, you can use common logs. You can set the bases to whatever you want. But normally it's using common logs, so you can use a log key on your calculator. So approximately 9.6 years. Now chances are, this will be continually changing. So it's not like an interest question where it only happens at certain times. This is continually changing, so that is an accurate answer. Example 2 says in 2002, the population of the city was 160,000 and was increasing at an annual rate of 4.5%. Write an equation to represent the population of the city as a function of the number of years since 2002. So P, the population, again, using that exponential function formula, which is y equals a times b to the power t over p. So instead of y equals, let's say p equals for the population. A is the initial number, which is 160,000. B, our growth factor, because it's increasing at a rate of 4.5%. That means you're going to have 100% plus 4.5% more. That'll be 1.045. And if we're going to use this formula, t is the time over p, the growth period is every 1 year. Yes?
So if it's like with this situation where it's like 2005, you just have to subtract it then?
Since 2002.
To subtract the year by the...
Well, that's now we're in part B. We're not there yet. We're just doing the equation right now. But the population in year 1, that'll be 3 years from 2002. This equation represents the population since 2002, when the population was 160,000. So for 2005, that's 3 years down the road. So we're going to let t equal 3. And once again, we can put this in our calculator in one step. And the population is 182,586. Let's round it to 587. I don't think it tells us what to round it to. No, so we'll just round to the nearest person. If the population continues to grow at this rate, how many years would it take for the population to double? So that means that the number at the end would be 320,000. And that'll equal 160,000 times 1.045 to the power of t. And we're going to solve for t. So we would divide both sides by the 160,000, which will give us 2 on the left. And once again, to solve this, we would convert from exponential to logarithmic. We'd start with the base and cycle through. It'll be the log with the base of 1.045 of 2 equals t. So using the change of base identity, log with a base of 1.045 of 2 gives us approximately 15.7 years. That's how long it would take for the population to double. Okay, a certain strain of bacteria doubles every 6 hours. If the number of original bacteria was 350, how many would be present after 28? So again, we're going to use the exponential function equation, where a is the original amount, which is 350. And because it's doubling every 6 hours, our growth factor is 2 because it's doubling. T, the time, is 28 hours over P, the growth period, is every 6 hours. So that's what we would use for our formula. If it doubles every 6 hours, then in 28 hours, if we go 28 divided by 6, that's how many times it will have doubled. Right? But we can put this entire expression in our calculator to do it all in one step. You have to put that entire decimal 28 over 6 in there. Right, we went 28 by 6 and we got 4 2/3, 4.6 repeating. If you just put 4.7 in for t, you're going to get a different answer. Okay. So if we round to the nearest bacteria, approximately 88, 89. Okay, example 4, patient who's feeling ill had a sample of bacteria taken from her throat. The sample contained 354 cells. 24 hours later, the sample was recounted and found to contain 8,186 cells. Determine the doubling period of the bacteria to the nearest tenth of an hour. So Y, remember, is the number at the end, which in this case is our 8186. She started with 354 cells, and because we want to know what the doubling period is, that means the number of cells is doubling every so often, and we want to find out what that period is, every so often is. The time that had elapsed was 24. Again, we want to know what P is. What is the doubling period or the growth period? So we can start by dividing both sides by 354, and that'll give us the exponential part by itself. Which gives us a decimal that we're going to have to keep in our calculator. So let me store that into memory slot A, because we're going to have to use that number again. But if you're writing it down, we'll say it's approximately 23.1 equals 2 to the power 24 over P. And once again, we will change it from exponential to logarithmic. We'll start with the base and cycle through. So log base 2 of 23.1 must equal 24 over P. Before I go to my calculator, let's get P by itself. First, by multiplying both sides by P. And then divide both sides by the log to get P by itself. So it'll be 24 divided by log base 2 of our 23.1 decimal that we have stored into memory slot A. So it's 24 divided by, again, I'm going to get my log function here, log base 2 of the value I put in memory slot A. So approximately 5.3 hours to the nearest tenth of an hour. That is the doubling period. Right? The value of P, the growth period. A radioactive isotope has a half-life of approximately 30 minutes. How long would it take for 320 milligrams to decay down to 10 milligrams? So again, we'll start with this exponential function. The number at the end is 10, and the number at the beginning is 320. And because we have a half-life, that means the amount of this isotope is being cut in half. We're told that happens every 30 minutes. How long will it take? So we want to know what T is, the time it'll take for the 320 to decay down to 10. So we need to solve for T. I would start by dividing both sides by 320. So 0.03125 will equal 1/2 to the power T over 30. And again, to solve for T, we would start by converting from exponential to logarithmic. We'll start with the base and cycle through. It'll be the log of 1/2 or the log of 0.5 of 0.03125 equals T over 30. So in this case, we would multiply both sides by 30 to get T by itself. And then go to the calculator. Whoops. 30 times log with a base of 0.5 of our previous answer, that decimal. So 150 minutes exactly. Because in this case, after 30 minutes, it'll go from 320 down to 160, half, after the first 30 minutes. After the next 30 minutes, after 60 minutes, you'll be down to 80, half of the 160. After 1 hour and 30 minutes, you'll be down to 40. So 1 hour and 30 minutes is 100, or 90 minutes, I should say. So at 90 minutes, you're down to 60. Another 30, which is 120 minutes, you'd be down to, let me do this again. I went from 320 down to 160 after 30. After 60, you'll be at 80. After 90, you'll be at 40. After 120, you'll be at 20. And then at 150, you'll be at 10. So this one, I mean, you could definitely check your answer just by cutting in half every 30 minutes. They're not always going to work like this, where you're going to get an exact answer. Sometimes it does. Population of germs on a dirty countertop doubles every 25 minutes. How long would it take for the population to triple? So for this one here, we're not given an original amount, but we know that we need to triple. So we can start with whatever original amount we want. We can start with 1 bacteria, and then that'll become 3 bacteria. But it doubles every 25 minutes, so our base is 2. That's our growth factor. And our growth period is every 25 minutes. We want to know what T is. How long would it take for the population to triple? We could have started with 5 bacteria and then ended up with 15. It doesn't matter. No matter which number you start with, you're going to triple it to get the number to the left of the equal sign. And then when you divide both sides by A, you're going to get 3. No matter what number you start with, if you triple it, and then you divide both sides by the number you start with, you're always going to get 3. So if we convert from exponential to logarithmic, it'll be log base 2 of 3 equals t over 25. And then we would multiply both sides by 25 to get t by itself. So 25 times log base 2 of 3. So to the nearest minute, it would be 40 minutes. And example 7, in April of 1986, there was a nuclear accident in Chernobyl. It contaminated the atmosphere with quantities of radioactive iodine 131. So the nuclear reactor melted down, right? It got too hot, and it got so hot that it actually melted down, and then you released all this radioactive stuff into the air. And lots of people died. Lots of babies that were born after that were born with deformities. It was terrible. And there's still lasting effects from that accident. Okay, so the half-life is 8.1 days. Determine the number of days to the nearest day that it took for the level to reduce to 25% of the original level. So again, we'll use that formula. And in this case, the amount at the end will be 25% or 0.25 times what we started with. So y will be replaced with 0.25a. A is the amount you started with. We want to know how long it took for the level to reduce to 25% of the original level, or 0.25 times a. Because the radioactive iodine has a half-life, our base is a half. We want to know how long it took, so we want to know what t is if the half-life is 8.1 days. You can divide both sides by the a, and they will cancel. So now we will convert from exponential to logarithmic. It'll be log with a base of a half of 0.25 equals t over 8.1. And we would solve for t by multiplying both sides by 8.1. So 8.1 times log of with a base of 0.5 of 0.25. So approximately 16 days to the nearest day. Remember that T and P are in the same unit. The half-life is in days, so the time would be in days as well. Yes.
In last one, when we were given like the stuff, we just kind of like
We weren't given what A was, but we were told we wanted to see how long it took so that there was 25% of what you started with. Pardon me? What would you do for number 7? No, it's not the same. In this example we just did, we were told we wanted to have 25% of the original level. So yeah, you could, if you wanted to, you could start with, say, 4 to begin with, and then you'd have 1 at the end. You could, yeah. It worked the same. You get 0.25 on the left. So yes, you absolutely could. All right, so there are some questions in a worksheet that follow. I will put the solutions on Google Classroom if you want to go through those for practice. Okay, there's 3 pages there that follow that lesson, and I will put those solutions on Google Classroom so that you can check your answers. Okay, but now we're going to go through the quiz.